Okay.
Okay. Thank you, Marco. I would like to welcome all of you also this afternoon to this third event of the program that we have dedicated to the inspiring speeches in the field of aerospace technologies that is entitled Rediscovering the Space. As I like to mention every time when we firstly started thinking at this series of speeches, we had our attention on the diversity of the contribution that will come for very different fields and experiences, including private companies, research centers, and also university, as is the case this afternoon. Today we have the contribution of Professor Giulio Avanzini, that is Professor of Flight Mechanics at the University of Salento. And as you probably already know, my university, Politecnico di Bari and University of Salento, have two joint inter-university courses in aerospace engineering. We have a first-level degree in engineering of aerospace system and a second-level degree in aerospace engineering. I've been knowing Giulio Avanzini in the last years because we together we have designed a part of these inter-university courses, and something that we have in common, me and Giulio Avanzini, is both of us, we agreed always in the opportunity of bringing in the aerospace engineering topics that are typically found in other degree, typically coming from information engineering or electrical engineering fields. Today, Giulio will talk us about the possible application of electric propulsion systems in airplanes, spacecraft, and extraterrestrial rovers. That is a very interesting topic in which I've been personally involved as a researcher in the last years. And I also hope that his speech and this topic will be interesting for all of you during this afternoon. I hope that really, as the name that we decided to put at this series of speeches, that also this speech this afternoon could be of real inspiration for all of you. And I just have to thank the Professor Avanzini for his availability this afternoon, and I give the stage to Marco De Tullio for a brief introduction of our initiative.
Thank you, Francesco, and good evening, everyone. So welcome back to this, that has been now a periodic appointment with this cycle of seminars. I thank all of you for being here again. And on my side, I have to admit that this is becoming an eagerly awaited appointment in order to meet experts in the field, to learn new things about different aspects of the aerospace field and to stimulate discussion. So I hope it would be the same for all of you, all of the participants. I see many of you connected, so please make the most of this opportunity, asking questions to our speaker or making comments. After the talk, in order to interact with the speaker, please write on the chat box asking to participate, and we will assign you the permissions to talk and make questions to Giulio. Thanks. So now I'm introducing Giuseppe Pascazio, Professor of Fluid Dynamics at Politecnico di Bari, who will act as a moderator of the event and will introduce today's speaker, Giulio, as Francesco also did. So Giulio, thanks a lot for being available. It's a pleasure to listen to you, and hope all of you can enjoy the seminar. Pino, go ahead, thanks.
Thank you, Marco. Thanks also, Francesco. And thank you also for this great initiative, but it's really inspiring. I mean, I did not have the opportunity to follow the previous one, but thanks to Giulio, I will start today. For those of you who don't know him, Professor Avanzini is, as I said, as already said by Francesco, is professor of fluid mechanics at the University of Salento. He got a master degree in aeronautical engineering and then the PhD in applied mechanics at University of Rome some years ago, and then he moved for say almost 10 years, I guess, at Politecnico di Torino, where he was teaching atmospheric and space flight mechanics. Then in 2011, he joined the University of Salento, where he teaches fluid mechanics and aircraft design. And he has also strong links with other universities all over the Europe and in the US. In fact, he was visiting professor at Glasgow University and University of Illinois. His main research activities, maybe Giulio will correct me, but main research activity was on rotorcraft simulation and control, autonomous flight, and spacecraft attitude dynamics and control. More recently, he also worked on autonomous underwater vehicles and performance and sizing of electrical and hybrid electric aircraft and rotorcraft, and electric propulsion in space, which actually is the topic of his talk today. From my side, I mean, I know Giulio is a well-known scholar and colleague in the Italian and international aerospace community, and I'm really pleased to moderate today's event, hosting his speech. Thank you again, Giulio, and the podium is yours, even if virtual. And
this is Francesco speaking. Just if I can add something that I missed before.
Yeah, of course.
Giulio, I really hope that this will be a first step for more strong involvement of you and the colleagues at the University of Salento in this new PhD program that we started together with the University of Bari, you know, in aerospace science and engineering. I think that we have to act like a single university system in Apulia. In Apulia region, there are not many researchers active in the field of aerospace science and engineering. We have to put together our efforts in order to reach more important goals. You know, thank you again.
Okay, thank you, Francesco. And this is exactly the reason for I immediately accepted the invitation from Marco De Tullio when he first offered me the opportunity to contribute to this series of inspirational speeches. I strongly believe that we have to act together, coordinate our initiatives. And so I'm just trying to give strength to this objective. And so we hope to tighten our relations, and with you in particular, Francesco, right, that the quality of electrical machines is crucial for the decarbonization of aviation, as we are going to see in a few minutes. So I can start sharing my screen if you agree, so that we can see the presentation. And is it okay for all of you? You can, yes? Okay, so what I'm going to entertain you with today is how the possibility of a fully electrical propulsion system on new categories of aircraft will pave the way to a very radical change in the paradigms of aeronautical and space transportation systems. Now, the first question is why, of course. Why do we need to go electric? Of course, there's an immediate knowledge of the fact that, as we know from the automotive domain, we love to say that there's no emission and less noise. So this kind of propulsion system is more green but this is true only for atmospheric applications. In space, pollution is not an issue, but of course, in space, electricity is the only renewable source of energy. So it's crucial that you use electrical energy as much as possible on board of spacecraft. Because when you run out of fuel in space, you cannot just go to the gas station and pump some more fuel and go on. You have to stop and end your operations. For all applications, electrical machines provide a very efficient energy conversion, and it is highly reliable. It's so reliable that until 15 years ago, you could find in Milan all carriages going on the railway that were more than 100 years old. And so it's really something very durable in time. But of course, there's an issue. How can we go electric? Now, as far as the atmospheric domain is concerned, we all know that most of the drones currently used in many civil and military applications are electrically driven. So it's possible to fly a full electric vehicle. But can we do that for a manned aircraft, which is of course much larger and has very stringent safety requirements? Up to which size we can build efficient and sufficiently light full electric powertrains, or is a hybrid electric powertrain an option? So these will be some of the discussions that I will try to point out, and trying to get also some questions from the floor. In space, electricity, as I said, is the primary source of power for most of the systems on board of a satellite, but electrical propulsion is changing once again the paradigm in space mission analysis and design. It is possible on a theoretical ground to have a fully electrical spacecraft in lower orbit without the need for any propulsion system. But this will need the development of very peculiar control loads. And that's something I've been working on in the last 15 years. And finally, I will try to highlight which are the issues for extraterrestrial rovers that will be one of the key elements in the possibility of having permanent bases on the moon first, and possibly the next 30 years on Mars. Now, of course, already from these very few initial notes, it's clear that this kind of revolution in changing, in totally revising the technologies at the basis of aerospace propulsion systems will require a multidisciplinary approach involving a lot of engineering disciplines, ranging from truly aerospace domain up to electrical conversion system, power management, power electronics, and measurements and sensors and whatever. So it's a huge field. So I will concentrate, of course, on what I know better, which is my own point of view as a flight dynamicist. I'm worried about how can we contribute providing a reasonably accurate but simple models that can account for the effects of using a totally different type of propulsion system on board of an aircraft, or a totally different type of actuators on board of a spacecraft. We need to estimate performance to see if a mission is feasible, and at the same time, provided propulsion plays a key role in every type of aerospace vehicle, we need to design the best possible configuration. So sizing and design need to accommodate a total change of paradigm in the definition of this novel class of aerial and space vehicles. At the same time, we will require different control loads for guidance and control, and this is true especially in space, where we're going to see that the effect of using electrical low thrust propulsion or fully electric control totally changes the scenario for controlling both orbit and attitude of a spacecraft. Now, to make you understand how deep is the change in the role that all the equations that we've been using for more than 100 years in designing aircraft is, we start from a very well-known equation. The first manned flight of a powered aircraft took place in the United States in 1903, and it was only 250 meters long. So it was pretty short, but only 5 years later, there were more than 500 flying machines in the world. And only 12 years later, most of the larger countries had an air force. So it was a very sudden development. And in a few years, it was necessary to design these vehicles. And so we can see that it was necessary to understand how much fuel, for example, do we need for performing a certain mission. And Monsieur Breguet developed his very famous equation, the Breguet range equation, which is reported on all flight mechanics textbooks. Now, this equation has been updated in the 50s for turbojets. So when we converted most of civil aviation from the use of piston engines to the use of turbojet aircraft, it was easy. We changed the type of engine, but still we can derive an equation that tells us how much distance can we cover in a flight using a certain amount of fuel, where this parameter zeta is called the fuel weight fraction, represent the amount of fuel scaled with respect to the initial fuel of the aircraft at the beginning of the cruise. Now, these equations are based on the fact that you are burning fuel in the engine. And this equation is at the basis of all the initial sizing process of any civil aircraft. I have scanned a page of the book I'm using in my own aircraft design course, which is Dr. Reimer's Aircraft Design, a Conceptual Approach book, which is very well known all over the world. And if you see the process for sizing the aircraft, which means to determine how much structure, weight, how much payload can we accommodate, how much fuel do we need for performing a certain mission, well, the process is based on the inversion of Breguet equation, so that given the amount of distance that we want to cover, we can determine how much fuel do we need. And from this, we build up the so-called weight fractions that, summing up and multiplying them up, we get the total amount of fuel that we need for the full sizing mission. Now, when you're flying with a battery-powered aircraft, the first thing that comes to the mind is that you're not losing weight during flight. So one of the first things that changes for the flight dynamics is that instead of having an aircraft that runs out of fuel and so gets lighter while flying, now we have a totally perfectly constant weight. A battery has exactly the same weight if it is fully charged or totally clear. So in 2011, this German professor who moved to the United States published 6 months. I was working on the same topic, and while I was delivering the paper, me and my colleague found out that he already obtained the result that we were close to publishing. So Traub equation, which is the equivalent of Breguet equation, is named after this German professor, and gives you exactly the same ingredients for a battery-powered aircraft, where here you have the voltage and capacity of the battery pack. Here you have the total efficiency of the transmission system, and this is the rated nominal discharge time of the battery pack. And Traub worked using Poincare equation, which is a way of estimating the amount of the actual charge, the real charge that you can extract from a battery, including an estimate of charge loss because of internal resistance of the battery. with a colleague of mine, Professor Giulietti, we analyzed this equation and provide a guideline for determining the maximum range under these conditions. So what we did was to use this equation and say, okay, we can determine analytically which is the best range condition, which is the best range velocity that allow us to maximize the distance flown given this discharge process, which is not the standard maximum efficiency as it happens in conventional piston prop driven aircraft. But this assumption, constant voltage and constant current, is an approximation of reality, because we know that during the discharge, the voltage of a battery will decrease. And so depending on how fast is the discharge, so how much power are you extracting from the battery, the decrease of the voltage of the battery will be also faster. So that the duration of the battery does not scale linearly with the power absorbed, and you need for the constant power, and if you fly at constant velocity with a constant weight aircraft, the power that you need is constant in time. Provided the voltage of the battery is decreasing, you need an increasingly higher current intensity for feeding your electrical motor. And so this changes something which is relevant to the overall performance that you expect from this kind of aircraft. And so we developed a very detailed study, an empirical study for classical lithium polymer batteries used on remotely piloted aircraft. And we derived an empirical model for constant power discharge processes, which accounts for this real life behavior of the battery. And by means of this model, it was possible to determine not only the best range and best endurance conditions, which means the condition in which we can maximize the duration of the flight or the distance flown, but we also had a quantitative estimate, for example, of the optimal battery pack. And as a difference with respect to conventional carbon-fueled aircraft, which is something very annoying. On an aircraft, on a conventional aircraft, if you load more fuel, you will fly a longer cruise. It's always true. It may be not optimal, but it will be longer. Now, if you add battery weight to an aircraft, you will get a maximum, which means that if you add more battery weight, beyond a certain limit, the amount of power that you're going to expect to spend during the whole mission, because you are flying a heavier aircraft, is going to overtake the advantage of having more available charge. And this is true for both endurance, on the left plot, the time of flight, and the distance flown. And there's another aspect. If you see the maximum here, it's very flat. So if this maximum is so flat, there's no point in making the aircraft heavier from 10 to 25 kilograms. You just make it heavier without any actual advantages. You just gain little more than 5% of range, making the total weight more than double. So there's no actual advantage in pushing this design. And so we also developed a technique for sizing an aircraft, including an estimate of best range and best endurance that can be combined together for determining the overall optimal configuration. Now, were these kind of approaches applied in real life? Well, as a matter of fact, up to this point, most of the purely electrical aircraft are experimental vehicles. And here we have two examples. On the top left corner, we have the Helios platform developed by NASA, which was the first attempt of the so-called atmospheric satellite. You know that you can observe Earth from space, and this is very useful because spacecraft can fly for many years. But of course, they are also very distant. If you're flying a low Earth orbit, you are beyond 250 kilometers from the Earth's surface. If you are closer to the Earth's surface, then you can get a better resolution in pictures. So it would be very interesting to have an aircraft which is capable of unlimited endurance. And this is potentially true if you use the whole side of the wing for solar panels, and if the aircraft has a zero average energy consumption between day, when it can load the batteries, and night, when it can on one side glide and at the same time lose a little bit of altitude, you can make a cycle between night and day with an average zero loss of altitude. So this was the first experiment for a very long endurance aircraft, and it went up to, if I'm not wrong, to 72 hours. On the bottom right corner, we had the very well-known solar impulse. The achievement of the solar impulse team was followed by all the media of the world, also outside of the aerospace community. You could find you can find in most of the news during the flight all around the world. This was the first aircraft that flew all around the world, powered just by solar cells. Of course, it had to land and take off, but it completed a global cruise around the world. But do we think that there will be something like that in the future? Now, for a rotary wing aircraft, so if we consider multi-rotor platforms, we have a lot of small-sized drones that are fully electrically driven. We have some prototypes, like the central here, but we have very serious companies like Airbus and the Italian Ital Design, which is the former Giugiaro Design in Torino, based in Torino, that is now a part of the Volkswagen Audi network. And so they designed this pop-up aircraft. And the pop-up aircraft is what is called a personal air mobility platform, which was based on a combination of multi-rotor that could raise the cockpit of this vehicle, fly it in an urban environment, and then deliver it to a carriage that can move on the ground. This is an artist view, but a prototype of this vehicle was actually flown in Dubai 3 years ago, but then Airbus gave up the project because of its cost. But it's something that it's feasible with current days technologies. On the fixed wing aircraft side, we have already many small-sized platforms, but the central picture here is our astronaut Maurizio Cheli, who with his startup, which is also based in Torino, which is Sky Spark, flew the first fully electric powered fixed wing aircraft with a manned flight of more than 2 hours and a half. More than 1 hour and a half. A few years ago, using a fuel cell. But on the top right corner, on the bottom, right corner, we can see another very interesting prototype, which is NASA X-57, which is based on an Italian aircraft, which is produced in Naples. And here you can see one of the advantages, of the potential advantages of using electrical power, because we can go with electricity, we can use with the so-called distributed propulsion, which means that we have smaller engines that can increase the dynamic pressure on the wing so that we can fly the same aircraft with a smaller wing. So as you see, we change completely the configuration with respect to conventional aircraft, using the advantage of possibly distributing power without the need of rotating shafts, gears, and whatever, just by means of wiring, which is much more efficient. Now, why are we not seeing all these electrical aircraft yet? we have many technological bottlenecks. First of all, battery energy density and battery and motor power densities. And this is where we need the help from Professor Cupertino and his community. Of course, fuel cells may represent an alternative, but you know that hydrogen is not easy to handle. But at the same time, we also need something to improve our understanding of the at low level of the behavior of batteries. Because if you fly a conventional aircraft, you always have exactly the idea of how much fuel have you in your tank, so how much time can you fly with that fuel. If you have a battery, the exact amount of charge, of residual charge available from a battery, will depend from recharge cycles, aging effects. It's much more difficult to estimate, but we need to be sure that we can land. There's another issue with certification. If we change the paradigm of manned flight, it's necessary to update certification procedures, and we need new materials and structures for optimizing these totally new configurations. We need tools for modeling a much more tightly coupled behavior of structure, flow, and propulsion systems. And if you don't do that, that's the risk. This is Helios after encountering a gust, and that's where Helios ended up. So if you don't take into account carefully modeling issues, you run the risk of losing control and crashing your very light structure. Is there a potential market right now? And the answer is yes. There is a potential market in general aviation, because if you go to general aviation aircraft, you see that most of the flight mission lasts less than 1 hour, and flying 1 hour a single or two pilots small size aircraft is possible. Also, hybrid electric general aviation aircraft is viable, but hybrid electric is something that needs to be very carefully considered. In the automotive domain, a hybrid powertrain is provides extreme advantages, because you can recover kinetic energy every time you brake. Now, if you consider the standard mission of an airplane, you don't have much variation of power. You usually have high power at takeoff and climbing, but then you spend most of the time cruising at constant speed. So you don't have power fluctuations that makes hybrid powertrain more efficient than a conventional piston engine based powertrain. So it's heavier because you have more components, it's more complex, and in terms of fuel advantage, if fuel saving, you have a little advantage. But of course, if you go to an electrical power system, you can use distributed propulsion, which provides you with serious advantages in terms of overall efficiency. And at the same time, you can imagine a novel type of procedure when you take off with electrical engine and the battery pack, so you have less noisy when you are close to the ground, and you reduce noise pollution. So it's still something interesting. We try to change the point of view, and with a colleague of mine from Università of Salento, Teresa Donateo, we analyzed another class of vehicles, which are Rotograph Helicopters in particular. And the helicopters usually have a much wider variation of power required during flight, and we consider hybrid configuration as a potential benefit for rotorcraft safety. Because if you have a hybrid powertrain, even if you have a very small endurance of 5 minutes, in case of engine failure, if the thermal engine fails and you have only one engine available on a single engine, the rotorcraft, you need to perform what is called the auto rotation maneuver, which is extremely hard, extremely difficult, and extremely dangerous, because you have to use the kinetic energy of the rotor for reducing the vertical speed component before touchdown. And this is something extremely difficult for a pilot to perform. We can use a hybrid electric powertrain, which with a battery, so that you perform most of the descent after engine failure in auto rotation, but then you switch on the electrical engine and you can stop the the descent rate by means of a powered touchdown. And this idea was awarded a prize, the Derek George Institute Safety in Aerospace Award 3 years ago. But let's change the environment and let's go to space, what in our beloved Enterprise movies, Star Trek movies, was the final frontier. Now, this is the view of when I was a kid. As Professor Pascazio said before, I got my PhD a few years ago. It's almost 25 years ago, to be precise. And I was a kid in the 70s. So when I was a kid, my parents bought a TV set, and one of the first things I saw was the Apollo mission. My copybooks covers were full of images of permanent bases on the moon, mission to Mars, very large space stations flying all around the Earth. So this was our imagination. And we've been to Mars, you don't know, but we've been to Mars many times at the cinema. Every couple of years, we have a new movie which tells us what would happen if we go to Mars. But as a matter of fact, we are still far from that objective, 30 years after going to the moon. Now, first of all, is there anything new in using electricity for propulsion in space? As I said at the very beginning of this talk, electricity is the primary power source on board of any spacecraft. And we can see from the top right corner, you have, this is Telstar 2, one of the first communication satellite, and these more squares are solar cells. Here you see GOES 7, the second, which has solar cell all around the spin stabilized body, main body of the spacecraft. And here we have a conventional geostationary communication spacecraft. And you can see that the size of solar panels for feeding the systems is significant with respect to the size of the spacecraft does. So there's nothing new in using electricity on board of a spacecraft. What is new is trying to substitute chemical propulsion with electrical propulsion. Because exactly as we have Breguet equation for fixed wing aircraft, we have something as important as Breguet equation in the rocket domain, which is Tsiolkovsky equation. And Tsiolkovsky equation is also known as Tsiolkovsky curves. It's called Tsiolkovsky curves because of this exponential relation. If you want to achieve orbital velocity, which is in the order of 7 kilometers per second, you need a lot of fuel. If you consider a rocket at the beginning of its flight, usually a percentage around 75% of the total weight of the rocket is fuel. So chemical propulsion allows us to reach space, but then once you are in space and your fuel runs off from the tanks, the mission is over. Now, the parameter that tells you the performance of a rocket engine is the so-called specific impulse. The specific impulse gives you the idea of how much impulse you can get per unit of weight of fuel burned. Now, if you consider the electric propulsion, the ideal scheme is exactly the same. A rocket engine works in this way. You have an amount of fuel, you burn it, you increase the energy, and then you eject it from a nozzle. Because of because of momentum conservation, you will get an increment of the residual mass of the vehicle because of the ejection of the fuel mass from the nozzle. Now, an electric thruster works exactly the same way, but this time you are not burning large amounts of fuel, you are accelerating very small mass of particles, usually ions or plasmas, but at very high speed, orders of tens of kilometers per second. Now, this can be done by means of electrostatic systems, electrothermal systems, or electromagnetic ones. I will not go into the technical details. I will just summarize the performance. If you consider the combustion of hydrogen and oxygen, which was, for example, at the basis of the propulsion system of the space shuttle, each one of the nozzles of the space shuttle could deliver 2 million newtons of thrust. you get a specific impulse in the order of 450 seconds. The Saturn V that went to the moon, each single engine, and there were 7 of them, was rated at 7 millions of Newton, with a combustion of kerosene and oxygen with a specific impulse of 350. If you use ion thruster or magnetoplasma dynamic thruster, you can go to thousands of seconds of specific impulse, which means a performance index that gives you much more impulse for much smaller fuel weight. But if you go to the other column, you see that the amount of thrust that you can get is in the order of millinewtons. There's no way for going to orbit the Earth by means of this thrust, but once you are in orbit, then you can make orbital maneuver or transfer to interplanetary trajectories by means of a much more efficient propulsion system, which requires a smaller mass of fuel for getting the same increment of velocity. And this is a huge advantage. But of course, there's a drawback. If you use high thrust chemical propulsion, the amount of time you keep your engine switched on is very small. So you can perform what is called the impulsive approximation of the maneuver. You move from one orbit to another one by switching on your thruster for a small amount of time, which is negligible with respect to the orbital period. So you can consider the maneuver as an impulse. If you consider low thrust electric propulsion, this is not longer true. You need to keep them switched on for longer periods of time. And so you have to change the whole set of techniques you use for designing and analyzing your mission. And there's another issue. You need solar panels. What is the solar radiance in space? It's in the order of 1,300 watts per square meter. The best solar panels have an efficiency of 30%. And moreover, solar panels usually degrade with time, and the radiance decreases with the square of the distance from the sun. So if you need 1 Newton of thrust from a magnetoplasma dynamic thruster, which requires 40 kilowatts of power per Newton of thrust, then you need 100 square meters of solar panels if you are close to the Earth. More than twice if you are in Mars, and 25 times that size if you are close to Jupiter. And that's the reason for missions to Mars are considering nuclear power as an option. Because of course, if you have a small nuclear reactor, you have electricity for a lot of time without the need of solar panels. Of course, the use of nuclear power poses other safety concerns, especially for manned missions. Now, as I said, most of the equipment on board of a spacecraft is driven by electricity. For example, the wheels by means of which we control attitude. Reaction and momentum wheels are the most widely used type of attitude actuator for controlling the orientation in space of the spacecraft, because it is based on a very simple principle. If I spin up the wheel on one side, I will get a variation of the angular velocity of the bus of the spacecraft in the opposite direction. So you exchange angular momentum between the wheel and the spacecraft by means of an electric motor. So electricity is renewable and I'm happy. I don't use fuel. But of course, in space, we have small but annoying perturbations. And so the actual value of the angular momentum is not constant. So because of the build-up of the angular momentum, sooner or later, we will reach the maximum angular speed of the wheel, and we have to desaturate them, and this requires fuel. Can we do something different? Yes, we can do something different using magnetic actuators. Magnetic actuators can work if you are sufficiently close to the Earth, in which case we are inside the magnetosphere. And we can produce an external torque by means of electrical energy instead of thrusters. Now there's a problem, and the magnetic torque is given by the cross product of the magnetic dipole produced by the magnetorquers times cross product the geomagnetic field. So we have no torque around the direction of B. So this kind of active control system is inherently under-actuated, which means I don't have the freedom of controlling at the same time all the 3 rotational degrees of freedom. And that's the reason for I've been working for many years with a colleague of mine from a university, with 2 colleagues of mine, Professor Giulietti and Professor De Angelis, on the use of magnetic actuators as a means for spacecraft active control without the need for external thrusters. And we have analyzed several maneuvers. I will just jump to the very final type of vehicle, which is the extraterrestrial rover. And once again, if you go to see the old NASA reports with the design of, for example, Curiosity rover or Opportunity, you will realize that they've been very effectively engineered, but the major driving factor was the possibility of taking them to Mars in a safe manner and guarantee they were probably working after landing. The attempt of optimizing performance has never been undertaken because other issues were considered more crucial to the success of the mission. Now, Curiosity has been working much longer than the expected operational lifetime, so it was absolutely a success. But if we want to reach Mars and provide future astronauts with actual heavy-duty vehicles, we need to optimize their performance. So we have run again the same type of approach we used for optimizing the sides of the electrical-driven fixed-wing aircraft. We use the same approach for optimizing a rover, and we demonstrate the validity of this approach by means of a campaign, of an experimental campaign on a terrestrial rover, but also by comparing our results with those obtained from the only rover that worked outside of our Earth, which is the lunar rover, which flew in mission Apollo from 14 to 17. So with a very simple model, we could develop these curves so that we can identify, depending also on soil condition, which is the best range condition. So as soon as we know where we're going to land, we can optimally size the battery pack for and so the overall configuration of our rover. So conclusion and future work. What do we expect? There's a major issue. We need better batteries. That's the crucial bottleneck for all the applications we've been discussing so far. So please try to find a way for getting more energy in less weight, and we will be extremely happy to go electric in air and space. So this ends my presentation.
Thank you, Giulio. Thank you very much. Very inspiring speech indeed. Also, the last slide is very is very beautiful. I appreciate it. So I opened the question session, and there is Maria Cinefra, that you know very well. Let's ask to make you a question. So please, Maria.
Thank you. Ciao Giulio.
Ciao Maria.
Thanks for your presentation. It was very interesting and nice. So I present myself just for other participants. I am associate professor here at Politecnico di Bari in aerospace structures. And I have a question for Giulio regarding my field. Because you already said in your presentation that from a structural point of view, you need lighter materials, lighter structures, I suppose, to compensate the drawback of the batteries, the weight of the batteries. So I was wondering if the composite can be a solution, or you need better materials, lighter materials. And on the other side, I suppose there are some requirements that, in the case of electrical propulsion, are less stringent, such as fire resistance or, for example, the vibrations. I suppose that in this case, the problem of vibrations is
less relevant.
So I don't know if you already, if there is someone already working in this sense, or in general there is the need of rethinking the structures in order to meet the objective of full electric propulsion.
If you want to use batteries, of course, composite provides you with a better option than the conventional metal structures. But there's an idea that is being considered, which is using the metal of the structure as one of the cathodes of the battery system.
Wow.
If you want to recharge the battery, you can convert part of the surface metal into oxidizing that, but then you can revert the process when recharging your battery, where one of the elements is given by the structure itself. And there's one option of using air as the cathode. So this metal air battery may open a perspective which is truly a revolution in the concept of air transportation. But if you consider conventional batteries, for example, the Sky Shark of Maurizio Cheli, it was a composite-based aircraft. So as far as conventional battery, electric motor, propeller configuration, powertrain is concerned, then composites are at present the most well-used option.
Perfect. Thank you. Very interesting. Thank you.
Thank you, Maria.
Waiting for the next question, I will do one by myself. And Giulio, you talked about the need for a multidisciplinary approach in this case. And I would like you to mention one of these, and this I will do also another one of these. Let me say one of the issues where you do really need first stage a multidisciplinary approach. And the second, you just mentioned it, but I want you to make some more comments on this topic. I mean, you just mentioned that the use of fuel cells. I mean, you mentioned that battery is let's say more efficient batteries, but what about fuel cells? You mentioned the difficulty in managing hydrogen on board, but I would ask you to discuss a little bit on this if you have some consideration apart from what you said.
Yep. Okay. The first aircraft which flew electrically powered was using fuel cells. So fuel cells are definitely one of the most widely researched options for energy storage on board of manned aircraft. And as a matter of fact, we hope to start a research in this area with the help of Anil Anzolla for measuring the performance of fuel cells in propulsion for small multi-rotor drones, and then to scale up to heavier rotorcraft. But in general, the most relevant difficulty is how to handle hydrogen, because you know that you have a weight penalty because of the very high pressure or extreme cold condition which you have to keep hydrogen. And I wouldn't say that it's like the famous airship that went from Berlin to New York, and this very well-known picture of this airship in flames. But of course, we are talking about much smaller quantities, and we have now composite tanks that can handle very high pressures. So in general, hydrogen can be handled, but still, in case of a crash, for example, which you have to take into account as a possibility, it's much more difficult to provide the same level of safety of cockpit resistance to this kind of event. You have to determine, when I say that we need a multidisciplinary approach, and which is okay. I would say that the concept of multidisciplinarity was born in the aerospace domain, because the aerospace domain, since the dawn of the aeronautical era, has been intrinsically multidisciplinary. Now the problem is that the number of disciplines that are required is getting larger. Now you need a very good set of information engineers, control engineers, as well as you need people with a background on materials or structures of flight mechanics. The amount of intelligence on board of a CPU of a conventional aircraft nowadays is huge. You have to control redundancy, recognize failures. You have very high-level tasks that you have to develop. Now, if you go to the to a totally new class of vehicles, you have to undertake from scratch an analysis, for example, of all the failure tree. So everything that has been done so far, and we have half a century of experience in the use, for example, of turbojet engines in the civil aviation domain, this becomes history. And you have to start once all over again for determining certification procedures, safety assessment, reliability assessment, on the basis of which you guide the design. So you need also people with a very good experience in statistics and projection of experimental data and whatever. So it's it's a very multidisciplinary challenge with a very wide spectrum of things required.
Thank you, Giulio. So I will ask next colleague Alfonso Maffezzori asked to make a question. He's an esteemed colleague from the University of Salento. Please, Alfonso.
Thank you, Giuseppe. Giulio, you gave us a very interesting presentation. Unfortunately, Giuseppe asked you about hydrogen power. That is one of the questions. I listened in the past to the to a Boeing conference where they presented the Phantom Eye, high altitude, long endurance vehicle that is hydrogen. It has hydrogen as fuel. And really, I think it could be an interesting approach. And I know that also Airbus with the zero emission project is going in that direction. But I understand that there are a lot of critical issues. Probably the one you mentioned that I was not thinking about is the safety in case of even small accidents, not too big accidents that can be catastrophic. But another point that is relevant that you mentioned is another idea that is not mine, that I listen around in conferences, and it was focused on electric cars. They noted that you have a weight for the structure and a weight for the battery, but in some way it could be really interesting to merge this function to make multifunctional materials, so a fraction of the structure could work as a battery, even if with the lower efficiency, but it could be really useful to save weight. I know that I know that in the past there was an European project on this, but I tried to read some conclusions, but not very interesting at the moment. I think that is very tricky point. This one. Can you further comment about this?
Yeah, this was one of the things that we discussed with Maria Cinetra. It's to transform part of the metal structure in an element of the battery. If you have a rechargeable battery, so you can revert the oxidization process. So less relevant parts that are not structurally relevant, for example, covers or elements that are not relevant from the structural point of view and use them. Also within composite, someone is thinking of making layers, and inside the layers use part of the materials as elements of the battery. Of course, it will be less efficient, but still it adds little, if any, weight to the design. So this is something that I have been discussing with some colleagues.
No, the main problem I saw, and I couldn't, I never had really support from electrochemists, that if you want to use composites, you need an electrolyte that has properties comparable to that of resin. And that means a solid electrolyte that is usually is not very performing from electrical point of view.
Okay.
Thank you.
Thank you, Alfonso. We have time for let's say 3 questions. First, I have to apologize because I lost the correct priority. Lorenzo Santoro, please, it's your time.
Thank you. I am a PhD student in mechanical engineering in the Polytechnic of Bari. Can you hear me?
Yep.
Okay. I would like to ask Professor a question. Lately, there is a talk about asteroids and their ability to provide fuel for space missions. So from this point of view, can asteroids be an obstacle or an advantage for electric propulsion in space?
Well,
please, Commander Spock.
The idea of mining asteroids is almost as old as spacecraft themselves. The first study of NASA on reaching asteroids and taking them close to the Earth orbit for reaching them more easily is in the 1957, if I'm not wrong. I was using that because they developed a very nice way for optimizing the mission with chemical thrusters towards the near belt of asteroids. And it's a very nice study. So I would say that this is clearly an option, but of course you have to compare the advantage of having something along the way with the difficulty of reaching that. If you, unfortunately, space is not like a highway for which you can go anywhere and you can stop whenever you like. You are along an orbit, you can change that orbit by using fuel or electrical propulsion, but every time you get close to a body, you need energy for slowing down, landing on the body, accelerate once again. So it's a very tricky travel. So the idea, this was the reason for the idea was that of taking the asteroid closer to the Earth before mining, so that you can perform the mining where you need. And this was one of the ideas for building the manned large-sized space stations. As far as the chemical components of the asteroids, that's another issue, because of course you have to understand which are the chemical elements inside the asteroid. Now there's been space geophysics has been developing very much in the last decades, but still we have no idea what's under the surface, for example, or we have little idea of what's under, below the surface. If you consider the fact that on Mars, which has been the most explored of our neighbors, the depth reached by the drilling machines of the rovers launched by the United States was, if I'm not wrong, less than half a meter, 1.5 feet, more or less, if I'm not wrong. So what inside an asteroid or inside a planet is still at least partially not exactly clear. We know how it is difficult to identify, or we have experience of how to identify elements on the Earth's surface, but doing that in space is much more difficult.
Okay, thank you. It's a very intriguing question and answer, of course. Next question is by Elena Ancona. Please, Elena is another PhD student. Elena, are you there?
Hi, yeah, can you hear me?
Yep. please.
So thanks a lot for the presentation. It was really I have a question regarding one of the disadvantages that the professor mentioned about the electrical propulsion in space. So the fact that the maneuver cannot be considered as impulsive anymore.
Yeah.
Are you currently involved in any study, let's say, for the optimization of those low thrust trajectories, or what is the state of the art from your perspective on this?
Okay, I've been working on that in the past. You know that there's the so-called Lambert problem, which is a very well-known problem in astrodynamics, which means the identification of an orbit that connects 2 points in space under the action of gravity only. So you have a semi-analytical solution for identifying an orbit that can fly for reaching a point in space in a given time. If you use a low thrust system, you are not flying a Keplerian orbit arc, and so you have to account for the slow variation of all orbital elements of your orbit. So one of the things that we have been working on is try to minimize the amount of calculations you need for estimating the value of orbit parameters after a finite arc under low thrust propulsion, in order to improve the efficiency of optimization algorithms. In general, optimization algorithm has been widely used in space mission analysis and design. There's a huge literature based on many different approaches. I've been not working with, but I've been, let's say, looking close to some of the most successful teams when I was in Torino. That my professor Colascurdo and his workers, who also won the global trajectory optimization twice against giants like NASA, or and they used the implicit formulation. Other guys, like my friends in Glasgow, they've been using evolutionary algorithms for tackling the same problems. If you go to low thrust propulsion system, the space of possible solution gets huge, so the difficulty in optimization gets even larger. So it's already a very hard problem with chemical propulsion, the optimization of a space trajectory, interplanetary trajectory. If you go with low thrust propulsion, things are even worse. And so what I've tried to contribute to was to try to simplify the mathematical representation of the effects of low thrust propulsion system by means of by application of a perturbation expansion approach to the Gauss equations of Gauss planetary equations. That's my contribution to the subject. But as far as I know, this is a very lively topic, and there are research groups working really all over the world on this topic, and that's one of the reasons for the global trajectory optimization challenge is becoming every year more successful. 10 years ago, there were 5 or 6 teams. Now, last time, we're 25, if I'm not wrong. So it's getting. I hope this information we're looking for.
Okay, we have time for. Thank you, Elena. And we have time for a last question by Davide Vittori. He's another PhD student. Please, Davide.
Hello, can you
hear me? You are.
And I assume you can see me as well. Okay, so first of all, thank you very much for the presentation. Super interesting. Yes, my name is Davide. I'm also a PhD student in aerospace engineering. I have a less technical question. So aside from the environmental friendliness and reduced noise, are there other benefits that are attributed to electric or hydrogen fueled aircraft? So for instance, in cars, obviously you have performance improvements, you have the experience itself, it's smoother, less, let's say, friction throughout the driving experience. So is there something similar within, or could there be something similar within aircraft?
Well, one of the things that will be worse is everything which is related to certification. This is what was one of the topics that just mentioned, and I didn't go into many details. in aerospace in general, but in aeronautical engineering in particular, every new technology is a nightmare from the certification point of view, because you have no previous experience for basing your reliability analysis. So if you totally change the paradigm of your propulsion system, then you lose your previous experience. So in this respect, there will be a transient time during which we need to build up our knowledge of the system to make it safe and adequate. You know that there's a very nice way of saying that takeoff is optional and landing is mandatory. So once you are in flight, you want that everything works very smoothly. So as currently Professor Cinefra said before, we do hope to reduce, for example, vibration loads, because of course electrical engine runs smoothly, and so you have less vibration from the engine side. But at the same time, if you have an electrical propulsion system, you need a propeller. Propeller will prevent you from reaching very high speed, for example. Now, as a matter of fact, Airbus is analyzing ducted fans, electrically driven, but still the technology is totally different. You cannot reach very high velocity even if you shroud the propeller. You will never reach the exhaust velocity of the thermal engine, of a turbine engine, by means of a pure fan-based system, even if it is ducted. So in this respect, this will put a very severe limitation on the maximum expected velocity, which of course will turn up in longer flight time. If you're flying from Rome to Milan or from Bari to Greece, you don't mind too much, because when you are below 1 hour and a half, the terminal phases will use a significant portion of the total mission time. But if you are flying from Milan to New York, then it's different. So in this respect, flight time is also an issue. And we expect a reduction of performance in this respect, instead of an improvement. So you have slower aircraft, which is not bad in general for short range missions, quieter, which is good, but you have to build up experience. One of the difficulties is that this kind of technology is more relevant for civil applications. Now, most of the technological advancement in the aerospace industry has been tested for years in the military domain before moving them to the civil aeronautical domain. And this was a very significant advantage. For example, composite materials have been used on the F-16 many years before there was a single piece of structure of any civil aviation jet certified for use on a route. Building on this experience in the military sector, it was possible to introduce the same technology with a total level of confidence on the behavior of these novel types of materials. Now we don't have this. The interest for reducing pollutant, for reducing noise, is typical of civil applications. They don't care about noise and usually and pollution. They have other objective functions. And so in this respect, we have to build up our own experience starting from smaller aircraft. And that's the reason for the experience that we are building on small drones that we move to larger aircraft, but still ultralight ones, and then to general aviation, and then regional aircraft will be a process which will take years probably. Both from the technological perspective, because we don't have technologies for long-haul flight with a fully electrically powered aircraft, but also because we need to build that experience.
Yeah, just to add a quick comment on that. I'm sure you're familiar with Lilium, the German company. They claim to have developed the first fully electric jet engine. Yeah. And they actually, I just saw a couple of days ago, they secured partnerships with airports in the United States already. So they're moving quite fast.
Yeah, but then certification is hard. There's always this bottleneck. Okay, you have to prove that your new technology guarantees the same level of safety for passengers, and that's the hardest part because you need many trials.
Okay, Thank you, Davide. We have time for the very last question by Giovanni Siroslabini. Please.
Okay.
Ciao, ciao.
Ciao. No, I put the question several minutes ago in the private chat with Giulio, so perhaps you missed it. No, there is obviously we are looking at Planetech Italia at the application side of electric propulsion. And there is one very interesting option that is the air-breathing electric propulsion in low orbit. I don't know if you had a look, because you didn't mention it during your presentation. That was very complete and very interesting. So I would like to comment on it.
It's I know that even my colleagues here in Salento are working on that. So there's a project I didn't mention because I try to be as complete as possible for the, let's say, current technologies with a focus on what I've been doing so far. And I'm not yet involved in that topic, but I hope I will be soon. That's a very interesting option when you exploit the uppermost layers of the atmosphere, trying to compensate for drag by means of an active thruster. And then, of course, will change the paradigm. So you will fly in a, exactly like going from below. We hope that we'll have atmospheric satellites like the Helios attempted to be. From the bottom, we hope to get lower from the top and try to fly lower orbit, exactly for the same reason. And this will require a peculiar system like the air-breathing space air-breathing propulsion system that is being analyzed in the framework of it's called NEAR project, if I'm not wrong. So that's, of course, really, it will, if it works, it will open a totally brand new scenario for Earth observations, of course. Even because it's faster, so you cycle many more times, you cover the Earth in a much more efficient way because you're flying a faster orbit.
If you are lower, also your optics works better.
Better solution, faster transfer. So it will be really something, a total change in Earth observation.
Okay, I guess we were over time, and I wish to thank a lot, really, Giulio, for his speech. It was very interesting. Also thanks to all the participants, and maybe there is still some hanging curiosity or question, but I will ask Giulio to accept eventually any email sent from the audience today and answering privately. I know he will accept it with surely. Thank you again to everybody. It was very interesting, particularly to Giulio. And the last word is to Marco, is the organizer. So please, Marco, thank you again to everybody.
Thanks, Pino. I really want to thank Giulio again for this very interesting speech. I see it has been very appreciated, and I also really enjoyed it. So thanks, Giulio. As you said at the beginning of your talk, we need to work together. So I think this is just a starting point.
I'm sure about that.
Okay, so thanks also to everybody for participating. Please, these 5 last minutes, let me make a little bit of advertisement in order to maintain the interest alive. I remind you of the next appointment on the 23rd of February with Giuseppe Cataldo from NASA Goddard Space Flight Center. And the talk will be about space telescopes, new eyes to explore the universe. So you see a little bit different from the talk of today, and this is the good thing of this cycle of seminars. We want to see the problem from a different points of view. So, Giulio, thanks again.
Thank you, everybody, for attending.
Hope to see you soon.
Same for me. See you, everybody. Bye-bye, and thank you for attending.
Ciao, bye.
Thank you.